Legend has it that when it rains for several days, it is because a dragon has left its lair in the forest and is flying across the river to the sea. This old story from the Casamance region of West Africa is no different from others around the world. The Amaru, a dragon creature of the Andean mythology in South America, the rainbow serpent of the Australian Aborigines, or the Chinese dragon, are all deities that control the weather. So let me tell you a story about our climate and the weather patterns that drive our lives, because rain, clouds, wind, they all affect us. Our crops, our food supply, our drinking water. The very basic things we need to survive depend on a very delicate balance, an atmospheric cycle that repeats itself every year, but can change at any time. Our fate depends on it. No wonder we have looked up at the sky and wondered who or what controls our destiny. According to Chinese mythology, dragons control the weather and the seasons. Though most dragons are wingless, male dragons possess the power to fly to the heavens and bring rain, while female dragons control earthly waters like rivers, lakes, seas, and wells. In Japanese mythology, dragons are often associated with the sky and are considered to be powerful celestial beings. They are said to have the ability to control the elements, such as rain and thunder, and are often depicted as being able to fly through the clouds. And in Korea, there's a saying that goes, "The rainbow is the trail of the dragon that has ascended to heaven." Today, we have the tools to study these atmospheric phenomena.
Every summer, we get circulation patterns around Asia that can affect the globe.
So ever since the satellite data showed that this large chemical signature in the upper atmosphere over the Asian monsoon, the community has been working on airborne research to study this phenomenon, study the region.
So ACCLIP is looking at material that has come up in the Asian region in storms, being vented upward, and then it's carried around in this, what we call anticyclonic circulation, or as you look down, the air moves around clockwise, but over a huge dimension, covering almost all of Asia, from Japan and Korea all the way over to the Middle East.
So the question is, what are the formation processes? How does it then basically spill out of the Asian summer monsoon anticyclone into the northern hemisphere?
At the autumnal equinox, according to one source, the majority of dragons descend into the sea where they hibernate for 6 months. At the vernal equinox, dragons leave the sea and ascend again into the clouds. Destructive typhoons and equinoctial hurricanes along the coast in the spring and autumn are caused by the disturbance of the waters when the great animals thus enter or leave their maritime home.
So Asian monsoon has been known by local people, by scientific community for a long time, a century at least. It's being known as a weather pattern, and people see the rainfall, see the wind direction change. And only recent years, we found that instead of just dropping things down, actually changed what's going up.
One of the questions that arose is, well, this is an interesting system, but what impact does it have on the larger atmosphere?
The Asian summer monsoon brings not only thunderstorms and rain, but also deep convection that can transport air and particles from the surface upward. This can have important effects on the composition and chemistry of the atmosphere, as these gases and particles produced down here at the surface interact with each other and with the upper layers.
So the Asian monsoon system starts from May to September, but the peak of this process we can see is going to be in July and August.
You start seeing these enhancements, and the circulation basically confines the emissions within this region, which has a large population and increasing emissions. Within this region, that sort of allows for some chemistry that doesn't happen in other places, as well as this very intense deep convection that can take those surface emissions and loft them to very high altitude.
So this is a huge circulation. So stuff comes up in thunderstorms and then cycles around this. That stuff moves around. It's like watching a weather system wobble around and pull back and forth, but it comes over Korea and Japan. And so we're using high altitude aircraft to measure that stuff as it moves over the Korea-Japan region.
In order to study the effects of this transported material, we have to look and go way up in the atmosphere. According to Japanese mythology, Rajin is the god of thunder, lightning, and storms. Always accompanied by Fujin, his brother, the god of wind. They live high above the clouds and control the elements. Rajin is often depicted beating his drum, summoning a treacherous storm, and luring a dragon from the darkness.
So the atmosphere is divided into what we call the troposphere. This is where all of our weather occurs. And the stratosphere is high up, 35,000 up to 100,000, 150,000 feet above us. So it's very high above us. The stratosphere contains the atmosphere's ozone layer. And ozone screens solar ultraviolet radiation. That's dangerous, but fortunately we have ozone to absorb that ultraviolet radiation.
The ACCLIP is actually a very important region for this kind of studies because the rapid economic growth in China or in India. So this country has actually become very large producers of the ozone depleting substances. Although even though the actual controlled use of the ozone depleting substance has been coming down, but there's alternative replacement gases of these compounds. So those still remain as very active research area. So part of the ACCLIP team wants to understand is how much emissions of these gases coming from these developing countries in there, what's the percentage of them getting to the stratosphere and can be transported around the world to destroy ozone.
The ozone layer is a very important part of our atmosphere as it screens out ultraviolet radiation, harmful to all organisms on the planet. But there are other particles, called aerosols, that can also affect the climate and especially the Earth's energy balance.
About a decade ago in satellite observations, one of the things that was noted was an enhanced aerosol layer occurring within the Asian summer monsoon. And that enhanced aerosol layer is occurring because of the nature of the tropopause within the Asian summer monsoon at a high altitude. And so one of the questions is, as air leaks out or spills out of the Asian summer monsoon, how does that aerosol then translate and affect the overall northern hemisphere stratospheric aerosol burden?
But how do aerosol particles affect the Earth's radiation budget?
So within the climate system, stratospheric aerosol basically plays a role in the planetary albedo, how much of the sunlight that impinges upon the Earth gets reflected back to space. So we see this in periods when we have a large or multiple volcanic eruptions that put a lot of material into the stratosphere, and we see significant increases in stratospheric aerosol optical depth and the amount of aerosol in the stratosphere. We can tell that the impact on the climate from that is that a lot more light gets reflected back into space. That radiation being reflected back means there's less radiation reaching the Earth, and it has implications for surface climate.
So all the chemical compounds and gases that are transported into the stratosphere can have a major impact on our atmosphere.
15% of the Northern Hemisphere stratospheric aerosol burden comes out of the Asian summer monsoon. So that's not insignificant. So stratospheric aerosol has radiative implications for the climate system. And if the Asian summer monsoon is in fact a significant source of aerosol to the Northern Hemisphere, then it has a significant impact on the climate system beyond the nature of the sort of meteorological system itself.
So Watam, who was a Taoist sage, once was seen to laugh to himself as he sat with closed eyes, and when asked why he laughed, said, "Just now in the monastery of Haiyin, 300 miles distance, there is a great feast going on. The priest stirring the huge kettle of bean gruel has tumbled in, but the others do not know this and are eating the soup." News came from the monastery later on that proved that what the sage had seen was actually true.
Any aircraft campaign that NASA does needs to be strongly tied to our satellite observations, since that's job one for NASA, is to provide satellite observations for studying Earth science. And the stratosphere is one of the areas where NASA has a long and quite successful history in doing these stratospheric observations.
Satellites give us a global view and can make many measurements from space, but others can escape their scrutiny.
Our satellite observations can see these strong signals from the Asian monsoonal circulation. We've known about it there for many years, but it's a difficult altitude range for the satellites to get all the information you really need.
The really thin cirrus clouds will be transparent to a lot of satellite observations. And so, satellite observations are fed into weather forecast models as to give you the initial condition. But these cirrus clouds can act as a contaminant that may not be included in some of the cloud clearing algorithms you use there. So by making these measurements, we can constrain, just what these thin cirrus clouds are like and, the overall particle sizes, and we can feed that back to what the satellite is showing you. And we've actually developed an algorithm that can identify these thin cloud layers much, much better. And it's these measurements that help us validate these satellite retrievals.
So when we combine the satellite data, which gives you kind of large-scale picture of what's going on, combine it with the fine-scale features that we get from the aircraft itself, that really helps us to advance the science a lot. So that it will allow us to look at the satellite data downstream and combine it with what we know about what's going on a finer scale from the ACCLIP campaign will help us to understand what's going on with the satellite data in the future and in the past.
There are processes in the atmosphere that are difficult to detect or measure from satellites. That's why scientists need to look closer in more detail. But how can they make these measurements?
Most people think of clouds near the ground, right? These puffy clouds, but cirrus clouds are very high. So we're talking 40, 50, 60,000 feet. The only way to make measurements there at those altitudes is with an aircraft that can fly well beyond the range of a traditional commercial aircraft.
None can predict their appearance. Their flight is beyond appraisal. These were holy and magical dragons, surrounding the palace with luminous radiance. For this campaign, our dragons above the clouds are the NASA WB-57 and the NSF G5 aircraft.
So this experiment is designed to use two research aircraft. These two research aircraft has different layer of sampling, also different capability in altitude and range.
One plane is the NSF G5 aircraft, and that plane can get up to about 48,000 feet, quite high. We have a second plane, it's the NASA WB-57F. It's an older plane, but that plane can get up to about 60,000 feet. So the one plane, the G5, covers all the way from the surface up to about 48,000 feet. And then the NASA WB-57 covers from about 48,000 feet up to 60,000 feet.
That's part of why the review process said we really need both planes, because we needed to understand what's going on from near the surface all the way up to 60,000 feet. So that's why we're both here.
But managing a campaign like this is quite a complex operation that requires a lot of coordination between both teams.
This project ACCLIP is very well organized in terms that NASA ESPO provides a lot of logistical support, which normally we would organize ourselves. So in this case, my role is more or less managing the G5 aspect with a great support from NASA for the rest of the logistics, such as shipping, lodging, transportation, parking of the aircraft, and all of these related support activities. The entire G5 team is probably 35 to 40 people, which includes scientists, and then the aircraft support team, which is the pilots, mechanics, technicians, project manager, and also software engineers.
So for this campaign, the G5 is an ideal platform to be used, primarily because we can reach into the stratosphere as high as into the mid 40,000 foot range, 45 to 47,000 feet. We can carry a range of instruments, science instruments with racks, with operators, with some of the students and other scientists that we have working with us here. And we can collect a range of data on different chemical components of the atmosphere at a range of altitudes, all the way from the surface, like I said, up into the mid-40s in altitude, with a range of about 3,000 miles. So we have the capability of going a pretty good distance to the east or south of the Japanese mainland, and then coming back up again. So we can get a 7 to 8 hours worth of data. These are pretty good capabilities.
All the data collected by the G5 team will be added to the project. It will then be combined with data from the other aircraft, the NASA WB-57.
The WB-57 is an extremely capable platform. One, because we have a very large wing, two very powerful engines, and a large payload capacity.
Yeah, we have pretty much 18 different experiments on board right now. It kind of depends how you break them up, just because some share pallets, some have the same beginning part of the name but are different experiments. But we have basically a full load. We've got 4 pods on the aircraft, 2 super pods, 2 spear pods. We've 4 pallets full of different equipment, and then also the forward and aft transition have experiments on them as well. And our antenna farm. So we've got stuff hanging off everywhere.
The NASA WB-57 can carry a large suite of instruments high into the stratosphere. But this capability comes with its own set of challenges for the pilot and the mission system operator.
So we wear the suit as a preventative measure. So if we lose cabin pressurization and we're at high altitude, then physiologically we would not have a lot of time of consciousness, and we would potentially pass out within a matter of a few seconds. And it's generally harder to fly an airplane if you're unconscious. So the suit keeps you conscious and keeps us the ability to maintain control of the aircraft if we lose cabin pressure at a high altitude. So this airplane is quite different than anything I had ever flown before. So definitely the largest wingspan and very unique performance capabilities. And as far as high altitude and the airspeed, it's just very different. It's a large control yoke instead of a center tactical stick that you would have in a fighter type aircraft. So very different aircraft.
The aircraft's a two-seat aircraft. The pilot sits in the front. He does most of the piloting things, as I call them. And then I sit in the back and I operate all the experiments. And so I have 2 computer screens, a keyboard, a mouse, power switches, control switches for all the experiments on board. So I'm sitting there talking to the ground and the scientists on the ground to get instructions from them on what they want me to do with their experiments. So our job is to keep those experiments healthy and recording data during the flight.
Good communication and coordination is required not only with the ground crew and scientists, but also with air traffic control.
We need to do a lot of coordination to be able to get these flights to work. We are flying in heavy, dense traffic airspace, so we can't just go where we want to go. So it takes a lot of coordination beforehand. Most of our profiles, when either we're a high altitude aircraft, most of where they want us to sample is not at the ultra high altitude. So we're doing vertical profiles. So when we do our descents and dwells and then climbs, we are transiting through the air traffic control structure. So we do have to be aware of airliner traffic around us. But every time we fly the WB-57, without fail, every single flight, we hear some airline pilot go, "What was that?" And they look up and they just see a very strange airplane. They usually think we're a highly classified platform, or just no, we just fly for NASA, and we're doing a lot of unique science missions with it.
He ascended the highest peak of all, which was like a tower of many stories. Before him lay a wide stretch of sea, with islands of the blessed standing out of the water, and long stretches of pleasant land in view. They were peopled with happy souls, some riding on cranes, some on the phoenix, some on the unicorn. Some were sitting on the clouds, some sailing by on the wind. So many and so startling were the things seen that he could never tell the tale of them. This is an excerpt from an early 17th century Korean folktale in which a young man is taken to contemplate the wonders of the world above the clouds. But what can we expect to find now that we have the means and technology to study the atmosphere?
There are many measurements that we're taking in this campaign. There are gases such as water vapor, which are really important. Turns out that the troposphere is very wet. There's a lot of water vapor molecules in the troposphere, and the stratosphere tends to be very dry, very few water vapor molecules in the stratosphere. So we can tell when we're in the stratosphere. We just see the water all of a sudden sharply falls off and we know we're in the stratosphere. Now, ozone, which screens ultraviolet radiation, is exactly the opposite. There's a lot of ozone in the stratosphere and not so much ozone down in the troposphere. So we can use ozone to also tell if we're in the stratosphere or we're in the troposphere. And in fact, the two kind of go hand in hand.
So we're targeting a large suite of trace gases. So our instrument is equipped to measure common species like carbon monoxide, which is a tracer, which is a marker of the surface air, and ozone, which is also associated with the active chemistry.
Now we also measure other things. Carbon dioxide, nitrous oxide, methane. All of these are important climate gases. On top of that, we measure all of these substances that can lead to ozone depletion.
During the ACCLIP campaign, a range of 50 to 60 different species will be measured, as well as the chemical composition of particles transported into the atmosphere by the Asian summer monsoon.
Now, why make these measurements in particular? Well, we're looking at issues like ozone depletion. There are man-made gases that can deplete the ozone layer. This is a critical gas for screening ultraviolet radiation. So we want to know what's going to happen to the ozone layer. Are there certain man-made gases that will accelerate ozone depletion? Are we seeing gases that have been controlled by international treaties? Are they falling off?
Chemical compounds transported into the stratosphere can have a major impact on the climate system. Many of them can be tracked by ground stations and are well known to the scientific community and the public because of the negative effects they can have on the ozone layer. They are called the Montreal Protocol control gases.
So for the, we call them the Montreal Protocol control gases. Those, we're not too much worried about those because we know we can learn about the emission of those gases from the ground-based network. But some of the non-controlled species, we call them very short-lived halogen compounds. We have seen an increased abundance of these gases. In particular, there's one compound we really care about. It's called dichloromethane.
Well, we use dichloromethane for a number of purposes. It can be used as a solvent for cleaning things, for example. And this gas has chlorine in it, and chlorine can deplete the ozone layer. So the levels of dichloromethane have been going up down here at the surface. We have measurements from stations. They tell us dichloromethane is increasing.
Compared to the very long-lived CFCs, everything gets into the stratosphere. However, with dichloromethane, because it's relatively short-lived, a fraction of it gets into the stratosphere. So we also want to know, using ACCLIP measurements, what the fraction is.
That's a key question to understand ozone depletion. Knowing the levels of these man-made gases, how much is getting from the surface down here, we have ground measurements down here, but how much gets into the upper atmosphere, into the upper troposphere, and into the stratosphere, where it can cause ozone depletion.
So we need to track not only the concentrations of these gases, but also their lifetimes to understand their impact on the atmosphere.
We also want to take a look at climate change and how our gas is affecting climate. Many of these gases have tremendous climate impacts. Carbon dioxide being, of course, a primary gas that's produced when we burn things. So you get carbon dioxide comes off of burning things. And we can make measurements of that to understand how we're impacting the Earth's surface weather and temperature.
To complicate matters further, it is not only gases and aerosol particles that can determine the warming or cooling effect on the Earth's surface, but also a particular type of cloud.
Cirrus clouds are very unique. They're the most abundant cloud on Earth, but they're also the only type of cloud that can both absorb and reflect radiation. So they have a warming and cooling effect depending on the conditions. The thing is, though, that the overall radiative component, so the role they play in the climate system, is not well constrained. And so by doing these measurements, we can put better bounds on the impact of cirrus clouds in the climate system And so the NASA WB57 allows us to get to 50, 60,000 feet. So here we can make direct measurements and get a sense of how large or small the cloud particles are and just how much of a radiative effect those really thin clouds have, because they're everywhere. They're covering large swaths of the globe.
So in addition to the 2 research aircraft, we also have a team launch the balloon sound from the ground. This balloon sound will cover a large vertical range all the way to 25 kilometers. So that covers the entire layer, starting from the boundary layer where the emissions happen, all the way to the stratosphere. And that helped the aircraft calibrate the vertical range of this layer and where the aircraft data will fit in. So it's a 3-dimensional process, yeah.
So, as you can see, trying to better understand our atmosphere is a complex issue that requires measuring, working together, and collecting huge amounts of data.
So airborne science missions like ACCLIP have a primary goal of improving our understanding of sort of fundamental aspects of the atmosphere and climate system. We make the measurements so that we can better understand the climate system, so that we can make better predictions of the climate system going forward. Climate change is and will be a critical issue, and how we respond to that requires information. And missions like ACCLIP and others similar that allow us to improve our understanding of the climate system provide that information so that we can have better climate models and rely on those to then make policy decisions, because we have a better idea of what the implications of various policy choices are.
The Dragon Gate is located at the top of a waterfall that cascades down from a legendary mountain. It is said that if a carp swims upstream and successfully jumps the waterfall, it will be transformed into a mighty dragon. Only by facing and overcoming great challenges can we achieve success.
The extensive measurements of chemical compounds from ACCLIP can be very useful in 2 ways. First of all, these measurements can be used to improve model representation of these gases as they are transferred into the atmosphere. In particular, the convective lofting that's transfer these things into the higher atmosphere. These measurements can also be used in chemical models to improve the emission estimates that are used as input for all these models.
I mean, we can use the measurements that we're making here to understand where the global models' aerosol parameterizations are working, where they aren't working, why there are discrepancies, and what we need to do in order to improve those models to make better predictions of aerosol and how that aerosol interacts with the climate system in the future.
All the data collected during the campaign will certainly help us to better understand how the atmosphere works. But contrary to the famous Asian proverb of the Dragon Gate, we need to work together to study such a complex system.
To study this system, it takes a very large community effort. And the airborne study resources are very rare and very precious. In order to pull the resources from the community together, it takes multi-agency collaboration. So eventually the project grew into 4 funding agencies. And in addition to NASA National Science Foundation, there's Naval Research Lab and also NOAA, and put in large resources for this experiment.
On the WB57, we have participation from not only my laboratory at NOAA, the Chemical Sciences Laboratory, which is contributing about 1/3 of the payload, but also participants from various NASA centers, universities, and international organizations, including a university and a research institute, all bringing their specific expertise in making measurements that, when we assemble it all together, will give us the picture of the atmosphere that we need in order to address the science questions.
So overall, we have more than 30 different institutions, universities, and coming from 5-6 different countries be part of the greater team of the project.
So this actually has a large participation that's worldwide now.
ACCLIP and other airborne campaigns will improve climate models and our knowledge of the complex processes that take place in the atmosphere on which we depend so much, so that we can better understand and protect this world we like to call home.